semigroup S, then R की power n, that is R composition, R that is n times, is left and right compatible, is left and right compatible for every n greater than equal to 1. So for this we have to prove Rn is left compatible and right compatible. So we take element here, for any, you see, for any A, S, T belonging to S, such that S comma T belonging to Rn, then there exist Z1, Z2 dots on Zn minus 1 belonging to S, such that S comma Z1 belonging to R, Z1 comma Z2 belonging to R dots on Zn minus 1 comma T belonging to R. Because see, this is a composition, so in between there exists some element such that S comma Z1, by definition of composition, S comma Z1 belongs to R, Z1 comma Z2 belongs to R, Zn minus 1 comma T belongs to R, correct? Now, as R is both left and right compatible, so we can just since R is left compatible, therefore you see A S comma A Z1 belongs to R, and A Z1 comma A Z2 belongs to R, and dots on A Zn minus 1 comma A T belongs to R, correct? So all these belongs to R, correct? So now you see there exists in between elements A Z1, between this and R and R. So AS comma A Z2 belongs to R composition R. In a similar fashion, since there are n minus 1 in between A Z1, A Z2, A Zn minus 1, so it implies further that AS comma AT belongs to R to power n, which implies that Rn is left compatible. Similarly, all of you can prove that it is right compatible. You multiply by A on right side, that is SA comma Z1A, Z1A comma Z2A, dots on Zn minus 1A comma TA belongs to R, and then you can just club all. So SA comma TA will goes in Rn, so Rn will become right compatible. So in this way Rn becomes both left and right compatible. So it means that what is the conclusion? That when R is both left and right compatible, then R ki power n is so. It is also right and left compatible. So we come back to the proposition 1.5.8. So basically in this problem what we have to do, we have to prove RCA. We have to show that we just write like this. Now we show that RCE is compatible. So it becomes congruence if we prove RCE is compatible. So what is basically RCE? RCE is what? This will be RC union RC inverse union just 1s. Infinity, or this is 1 to infinity RC union RC inverse union 1s e power n, or we write like this, it is from union 1 to infinity s ki power n, where s is what? RC union RC inverse union 1s. Now we show that SC is equal to S. So calculate SC. SC is what? RC union RC inverse union 1s C. As we have already done, that is R union SC is equal to RC union SC. In a similar, it can be generalized for 3 also. That is, it is equal to what? RC C union RC C union 1s C. Correct? By previous result. Now RCC is what? R by previous result. RC inverse C. Okay. RC inverse C. Now this is what? R inverse C C. And 1SC is what? 1S. We just write like this. Since RC C is equal to RC, it is RC, and 1SC is equal to 1S. Why? 1SC is equal to 1S. I left for all of you that how 1SC becomes equal to 1S. 1S is what? Equality relation, and if you multiply, isn't it? 1SC is equal to 1S. Verify this. Verify by all of you. Verify by yourselves. It is very trivial that 1SC is equal to 1S. How it is? So RCC is equal to RC by previous results. Now this is equal to, now you see R inverse C, C is will be again R inverse C. So it is what? RC union R inverse C union 1S. So basically this is what? This is what? This is S. You can again just write it as this is equal to RC union R inverse C union 1S. This is what? This is again S. Correct? Because this is RC inverse. This is RC inverse. RC inverse. Because in bracket you can write just R inverse C is equal to RC inverse. This we have already proved this thing. Correct? Now SC becomes equal to S. It implies what? It implies that S is left and right compatible. See, this proof involves the involvement of so many previous results. But when this question is asked in the long type of question, you have to prove all those results. For example, if this question is asked under 15 marks, then all you have to prove all previous results. And if it is asked in short type, then you can just state the statements, and using those statements you can prove. So it implies S is left and right compatible. Now it implies what? S ki power n is again left and right compatible. Also we have proved this also. So by previous result, when SC is equal to S, then S is left and right compatible, we have already done. And if S is left and right compatible, then S ki power n is also left and right compatible, we have done. Correct? So now you see, now if you take, when S ki power n becomes left and right compatible, then you see RCE becomes right and left compatible. How? You take any S comma T belonging to RCE, correct? Then it is equal to what? It will be 1 to infinity Sn, correct? It implies what? S comma T belonging to Sn. It implies what? That since Sn is what? Left and right compatible, it implies that Cs comma Ct and Sc comma St, Cs comma Ct and Sc comma Tc belongs to Sn. Why? Since Sn is what? Left and right compatible. Since Sn is left and right compatible. So Cs comma Ct belongs to Sn, Sc comma Tc belongs to Sn. So Sn is contained in where? It is contained in, of course, union 1 to infinity Sn, that is what? That is RCE. So we have proved basically Cs S comma T when belongs to RCE. We have proved that Cs comma Ct and Sc comma Tc is an RCE. It implies that RCE is compatible. And already we have know that RCE is the smallest equivalence relation, so it was equivalence relation already. So equivalence compatible relation, it implies that RCE is what? Equivalence relation. Equivalence relation containing R. Containing R. So sorry. Congruence relation, because it was equivalence and we have already proved compatible, so it is congruence relation. Congruence. So RCE is congruence relation containing R. Now what we have to prove? We have to prove that RCE is the smallest congruence relation containing R. So for this, what we do? Let T be another congruence relation containing R, correct? So R is contained in T. It implies that RC is contained in TC, correct? And TC is equal to what? T. Since T is congruence, T is being congruence, T is left and right compatible. When T is left and right compatible, then TC is equal to T. Since T is left and right compatible. Correct. So RC is again in contain, R is contained in T, RC is contained in T. It implies what? R union RC union 1s is contained in T. Correct. Basically we have to prove that RCE is contained in T. This is equal to what? This is basically S. S is contained in T. So S is contained in T. It means what? It implies that S is contained in T. So if you talk about Sn, Sn is contained in T. T, since T is transitive relation. Because see, when S is contained in T, then S composition S is contained in T composition T. You see, when S is contained in T, it implies that S square is equal to S composition S is contained in T composition T, and of course it is contained in T because T is transitive. In a similar way, it implies that S ki power n is contained in T. So S ki power n is contained in T. It implies that union Sn 1 to infinity, that is RCE, is contained in T. So it implies that RCE is equal to R sharp. That is the smallest congruence on S containing R. Proved. In this way, this big theorem is proved. Basically, they have proved by another funda, that is in book it is proved that they are saying that when RC is contained in T, correct? From here, when RC is contained in E, then it implies directly that RCE is contained in T. Why? Because RC is the smallest equivalence relation containing RC. So of course RCE is contained in T. So this is by proposition 1.4.9. So it's a good reason. It's a good reason. I think it is better you write all this. That is, when RC is contained in T, so RCE is the smallest relation, equivalence relation containing RC. So by proposition 1.4.9, RCE is contained in T. So in this way we have proved that. So in this way we have proved that RCE is the smallest congruence, because RC is also congruence. So it is the smallest congruence containing R. Now proposition 1.5.9, it is same like that, and all of you do by yourself. Proposition 5.9, proposition 1.5.9 is home assignment for all of you. It is simple. That is R be a relation on semigroup S, and let AB belongs to S, then AB belongs to R sharp if and only if either A is equal to B, or for some n in such a set of natural numbers there is a sequence A is equal to Z1 is connected to Z2, dots on it is connected to Zn is equal to B of elementary R transitions connecting A to B. correct? It is this theorem is same like as we have already done proposition 1.5.0, I think so, 1.4.10. We have already done 1.4.10. In the same fashion, all of you have to do 1.5.9. The same concept is there. So all of you try by yourself. Finally, I will do this proposition 1.5.0. Before that, A comma B belonging to S cross S such that for every xy belonging to S1, xay comma xby belongs to E. This is defined as E natural. This relation is defined as E, where E is what? E is equivalence relation on semigroup S. Then what is proposition 1.5.10? E natural is largest equivalence